This lesson is a part of the Google IT Automation with Python certificate, providing you with in-demand Python, Git, and IT automation skills to advance your career in IT. Get access to practice exercises, quizzes, discussion forums, job search help, and more on Coursera. And you can earn your official certificate. Visit grow.google/itcert to enroll in the full learning experience today.
In the next videos, we're going to focus on a bunch of new concepts. We're going to dive into object-oriented programming, which is a way of thinking about and implementing our code. We'll discuss how to create our own objects and how to use many of Python's interesting capabilities. We're going to learn a lot of new terminology too. As usual, we'll include cheat sheets in the references and in the readings for you to refer to whenever you need a quick refresher. And as always, if something isn't clear right away, remember that you can review the content and do the practice exercises as many times as you need. Okay, ready for your orientation on object-oriented programming? There's a lot to cover, so let's jump right in. Imagine you have to describe an apple to someone who's never seen one before. How would you do it? And what would you say? Besides that it's delicious. You might start off by saying that an apple is a type of fruit. You might talk about how there are lots of different kinds of apples, each with its own color, flavor, and name. Well, when you're explaining concepts to your computer, it's a good idea to approach it in a similar way. Your computer has no idea what an apple is, or even what a fruit can be. If you want your computer to understand these things, you have to describe them in your programs and scripts. Up to now, we've discussed elements of syntax like variables, functions, loops, and some more complex data structures like lists and dictionaries. These are powerful tools in an IT specialist's toolbox, but it can still be difficult to translate real-world concepts like what's an apple or what's a user account into programs. To make it easier for computers to understand these new concepts, Python uses a programming pattern called object-oriented programming, which models concepts using classes and objects. This is a flexible, powerful paradigm where classes represent and define concepts, while objects are instances of classes. In our apple example, we could have a class called apple that defines the characteristics of an apple. We could then have a bunch of instances of that apple class, which are the individual objects of that class. The idea of object-oriented programming might sound abstract and complex, but you've actually been using objects already without even realizing it. Almost everything in Python is an object. All of the numbers, strings, lists, and dictionaries we've seen so far and have used in our exercises and quizzes have been objects. And each of them was an instance of a class representing a concept. The core, apple pun intended, concept of object-oriented programming comes down to attributes and methods associated with a type. The attributes are the characteristics associated to a type, and the methods are the functions associated to a type. In the apple example, the attributes are the color and flavor. What would the methods be? Well, it depends on what we're going to do with the apple. We could maybe have a cut method that turns one whole apple into 4 slices. Or we could have an eat method that reduces the amount of apple available with every bite. Let's think about a more IT-focused example, like a file in our computer. A file has lots of attributes. It has a name, a size, the date it was created, permissions to access it, its contents, and a whole lot more. There are actually so many different file attributes that Python has multiple classes to deal with files. The typical file object focuses on the file's contents, and so this object has a bunch of methods to read and modify what's inside the file. Hopefully these examples help make object-oriented programming a little clearer. Remember how we used the type function when checking what type a certain variable was? Let's do that again now. When we use the type function, as we just did here, Python tells us which class the value or variable belongs to. And since this is a class, it has a bunch of attributes and methods associated with it. Let's take the string class for an example. In this case, the only attribute is the contents of the string. What about the methods? Well, in earlier videos, we looked at a bunch of methods provided by the string class, like upper, to create an uppercase version of the string, or isNumeric, which checks whether or not the contents are all numeric. Each string we've used in Python up to now has been a different instance of the string class. They all had the same methods, but the contents were different. This meant that the result of calling those methods was different also. You can get your computer to list all the attributes and methods in a class. To do that, just use the dir function. This gets the interpreter to print to the screen a list of all the attributes and methods. Whoa, that's a lot of items. Let's break this down a little bit so we all understand what's going on. The first bunch here are special methods that begin and end with double underscores. These methods aren't usually called by those weird names. Instead, they're called by some of the internal Python functions. For example, the _len__ method is called by the len function that we've used before to find out the length of a string. Or the __ge__ method is used to compare if one string is greater than or equal to another when using the greater than or equal to operator. After the special methods, we see a lot of string methods that we've already come across. This list gives the names of all the methods, but it doesn't tell us how we can use them. There's a different function to tell us that, which is called help. Let's give that one a go. When we use the help function on any variable or value, we're shown all the documentation for the corresponding class. In this case, we're looking at the documentation for the str class, the class of the string object. As before, it starts with the special method. If we scroll down, we reach the ones we've already seen. We can see the documentation for a bunch of methods, and it tells us the parameters that method receives and the type of return value. It also includes an explanation of what the method does. For the count method, we can see that it receives the substring that will be counted, and it has optional start and end arguments to indicate which slice of the string would be looked at. We know they're optional because they're written between square brackets. In general, being able to read and understand a method's documentation is super important when you're writing your own code. Using the dir and help functions puts all the documentation right at your fingertips. This makes it so much easier to figure out how to use something for the first time. When you're done looking at documentation, you can just type Q to quit. Python comes with a lot of classes already predefined for us, which is super useful. But the power of object-oriented programming is that we can also define our own classes with their own attributes and methods. While you might not need to do this when writing a simple script, as your programs grow in complexity, object-oriented programming will help you get the most out of the language. And that includes being able to define your own classes. We called out earlier that the point of object-oriented programming is to help define a real-world concept in a way that the computer understands. Defining a real-world concept in code can be tricky, so let's look at how we might go about representing a concept in Python code. We'll take it step by step and keep it simple. Let's take our apple example from earlier. We could use this code to define a basic apple class. Class apple pass. Sure, it doesn't look like much, but with these two lines we've defined our first class. Let's check out the syntax. In Python, we use the class reserved keyword to tell the computer that we're starting a new class. We follow this with the name of the class and a colon. The Python style guidelines recommend that class names should start with a capital letter, so we'll be using that convention. In this case, our class is called Apple. Class definitions follow the same pattern of other blocks we've seen before, like functions, loops, or conditional branches. After the line with the class definition comes the body of the class, which is indented to the right. In this case, we haven't added anything to the body yet, so we use the pass keyword to show that the body's empty. We can also use the same keyword as a placeholder in any empty Python block. So, how might we expand our definition of the Apple class? Well, it would probably have the same attributes that represent the information we want to associate with an apple, like color and flavor. We can add that information like this.
class apple. Color, we'll set that to an empty string. And same with flavor, we'll set that to an empty string for now.
So here we're defining two attributes, color and flavor. We define them as strings because that's what we expect these attributes to be. At the moment, they're empty strings since we don't know what values these attributes will have. See how we don't need the past keyword anymore now that we've got an actual body for the class? All right, now that we've got an apple class and some attributes, let's see our apple in action. Here, we're creating a new instance of our apple class and assigning it to a variable called Jonagold. Check out the syntax. To create a new instance of any class, we call the name of the class as if it were a function. Now that we've got our shiny new apple object, let's set the values of the attributes. All right, we've just set the color and the flavor as string values. To check that it worked, let's try retrieving them both and printing them to the screen.
Print jonagold.color. Print jonagold.flavor.
The syntax used to access the attributes is called dot notation because of the dot used in the expression. Dot notation lets you access any of the abilities that the object might have, called methods, or information that it might store, called attributes, like flavor. The attributes and methods of some objects can be other objects and can have attributes and methods of their own. For example, we could use the upper method to turn the string of the color attribute to uppercase.
So print jonagold.color.upper.
So far, we've created one instance of the apple class and set its attributes and checked that they are now correctly set. Now, we could create a new instance of the apple class with different attributes.
Golden equals apple. Golden.color, we'll set that to yellow. And golden.flavor equals soft.
Both Golden and Jonagold are instances of the apple class. They have the same attributes, color and flavor, but those attributes have different values. We called out earlier that we use methods to get objects to do stuff. We've seen several methods in our example so far, like lower for strings, append for lists, or values for dictionaries. The key to understanding methods is this. Methods are functions that operate on the attributes of a specific instance of a class. When we call the append method on a list, we're adding an element to the end of that specific list and not to any other lists. When we call the lower method on a string, we're making the contents of that specific string lowercase. How exactly does this happen? Let's take a closer look by defining our own methods. First, we need to define a class and create an instance of it, like we've done before. Nice! We've created a piglet class. While our new piglet might be cute, it can't do a whole lot right now. What if we wanted to give it a voice? For objects to perform actions, they need methods. And, as we called out before, a method is a function that operates on a single instance of an object. Let's add a method to our class. You can see here that we start defining a method with the def keyword, just like we would for a function. And see how the line with the def keyword is indented to the right inside the piglet class? That's how we define a function as a method of the class. This function is receiving a parameter called self. This parameter represents the instance that the method is being executed on. Okay, let's try this out and see what happens.
Hamlet equals piglet, hamlet.speak.
And the piglet goes, oink, oink. It sure does, but this makes the piglet say the same thing for all instances of the class. Boring. Let's make the method do something different depending on the attribute of the instance. This time, we've started the body of the class by defining an attribute called name with a default value of piglet. We can change that value later, but it's a good idea to set it now to make sure our variable is initialized. If you look closely at how we wrote the new speak method, you'll see that it's using the value of self.name to know what name to print. This means that it's accessing the attribute name from the current instance of Piglet. Let's try this out.
So we'll set Hamlet equals Piglet. Then we can say Hamlet.name, and we'll set the name to a string, Hamlet. And then we can call .speak on Hamlet.
Meet Hamlet, our Python pig. What, you didn't know pigs could talk? Well, they can in Python. In this example, the speak method printed the name Hamlet, which was the name attribute that we set. What if we create a new instance of the same class, but with a different name? It should generate a different output. Okay, let's try this out. I think Hamlet needs a friend. We've now created two instances of the Piglet class, each of them with their own name. When calling the speak method, each of them prints their name and not the other. Variables that have different values for different instances of the same class are called instance variables, just like the name variable in this example. Since methods are just functions that belong to a specific class, they can work as any other function, so they can receive more parameters and return values if needed. Let's check out what a method returning a value looks like. In this case, we've created a method that converts the age of our piglet to pig years. So the value that the method returns should change when we change the years attribute of our instance. Let's create an instance and check how this method works. Piggy is 2 years old in human years. How old is he in pig years? So, as the value of the years attribute changes, the return value of the pig years method changes too. Coming up, we're going to learn about a few special types of methods, including one in particular called constructor. Up to now, we've been creating classes with empty or default values in their attributes, and then setting the attribute values after we've created the object. This works, but it's not ideal. Working this way means we need to write a separate line for each attribute we want to set, and that makes it really easy to forget to set an important value. Us humans are pros at forgetting to do things, even important things. So when writing code, it's a good idea to do things early to prevent from forgetting them later on. So let's set those values as we create the instance. This way we know that our instance has all the important values in it from the moment it's created, and we don't have to worry about it. To do this, we need to use a special method called constructor. Let's go back to our Apple example to see this in action. The constructor of a class is the method that's called when you call the name of the class. It's always named init. You might remember that all methods that start and end with 2 underscores are special methods. Here, we've defined a constructor, one very important special method. This method, on top of the self variable that represents the instance, receives 2 more parameters, color and flavor. And then the method sets those values as the values of the current instance. Let's see how that works with a new instance of the Apple class.
Jonah Gold equals apple, and we'll give it red and sweet.
Great! And now let's check that all the attributes were set correctly.
Print jonahgold.color.
Perfect. So now by adding a constructor method that sets the attributes, we can create the class and have its values set right when it's created. Pretty handy, right? Constructors aren't the only special methods we can write. When we use the str or print functions to convert an object to a string, we are using a super useful special method. But before we go ahead and define one, let's see what happens when we don't define it. We just tried to print our Apple instance and we got a very weird message. We have the words apple and object in there, but what's the rest of it? Well, when we don't specify a way to print an object, Python uses the default method that prints the position where the object is stored in the computer's memory. This is definitely not what we wanted. If you ever try and print something and Python prints a random string of numbers and letters, you'll know that it's likely using the default representation, which is the position of the object in the computer's memory. So, how do we tell Python to print something that makes sense for us? We use the special str method, which returns the string that we want to print. Let's see what this looks like. By defining the special str method, we're telling Python that we want it to display when the print function is called with an instance of our class. Check it out.
Jonagold equals apple. We'll give it red and sweet. Print Jonagold.
So, the str method lets us print a friendly message instead of a bunch of numbers. In general, it's a good idea to think ahead and define the str method when creating objects that you want to print. There are a lot of other special methods. We're not going to look at the rest of them here, but you can find pointers to learn more about them in the official documentation. You'll find the link to that in the next reading. These concepts are new and not too easy, so don't worry if you're still trying to figure out the difference between a method and a function. We've all been there, and the best way to feel confident is to keep practicing until it's clear. You're doing great, so keep at it. The world of classes and methods can be a little puzzling when you're still learning your way around, and that's why the help function can come in handy. You might remember that we can still use the Python function help to find documentation about classes and methods. We can also do this on our own classes, methods, and functions. Let's check this out. We'll start with the Apple class we used before. And now we'll ask for some help. See how when we asked for help on our class, we got a list of the methods that are defined in the class? In this example, the defined methods are the constructor and the conversion to string. But this documentation is super short, and to be honest, it doesn't explain a whole lot. So let's go back to the interpreter by typing Q. We want our methods, classes, and functions to give us more information when we or someone else use the help function. We can do that by adding a docstring. A docstring is a brief text that explains what something does. Let's see how this works with a simple function. First off, we want to define the function.
So def, we'll call it 2 seconds, and we'll give it the parameters hours, minutes, and seconds.
After that, we add our docstring. We do this by typing a string between triple quotes, and we indent it to the right like the body of the function.
Returns the amount of seconds in the given hours, minutes, and seconds.
Next, we write the code for our function.
Return hours multiplied by 3600 plus minutes times 60 plus seconds.
So there we have it. We have a function with the docstring in its body. Let's see how we can use the help function to see it.
Help 2 seconds.
Success! The help function shows us the string we wrote. And as we called out earlier, we can add docstrings to classes and methods too. Let's use our Piglet class to see what this would look like. Now we've got a bunch of helpful information. We've added docstrings for our Piglet class and for its methods. Remember that the docstring always has to be indented at the same level of the block it's documenting. Docstrings are super helpful for figuring out how to use a function you've never used before. Not only that, if you're reading a piece of code written by someone else, docstrings let us understand the code much better because the classes, methods, and functions are clearly documented. So when writing your code, add docstrings to explain your functions, classes, and methods. It'll make a ton of difference to anyone who might use your code. In all our quizzes so far, we've been working with code blocks. Code blocks are a great tool for writing small snippets of code. But now we're tackling more complex problems, so we need a more powerful tool. We're going to start using a new tool called Jupyter Notebooks, kicking off with the next quiz. A Jupyter Notebook is a special kind of document that can contain pieces of programming code. We can execute these pieces of code inside the notebooks, one piece at a time. And the notebooks can also contain other things, like text, images, interactive widgets, and a whole lot more. These extra elements allow us to tell an interactive story with our code exercises. Like code blocks, Jupyter Notebooks lets us edit and run our code in the web browser. The difference is that we can add explanations in between the code, and also the pieces of code are related to each other. Jupyter Notebooks are an open source technology that you can use outside this platform. So if you're interested, you could even run it locally on your computer. So without further ado, let's check out how a Jupyter Notebook works and what you can do with it. We'll first click on Open Notebook and wait until the notebook loads. Now that it's loaded, you can see some explanatory text and a bit of code. We can execute the code by clicking the Run button in the toolbar. Or we can also run it by pressing Shift-Enter on our keyboard. Now that we've run our code, you can see there's a number here next to the first cell. This number tells us that the code has been executed. If a cell generates any output, it'll appear at the end of the cell. Let's try executing the next cell and see if we get an output. This cell includes some print calls, so after executing it, the interpreter printed the values. The comments in the code tell us that these values should be 9 and 1, but the print statements say that they're 0. That's because we need to edit the code in the first cell to make it do what it needs to do. Let's edit the goTo function. Once we've made the change, we need to re-execute the cell so that the elevator class is modified and an elevator variable is created with the new elevator class. And now we can re-execute the second cell. Okay, now we get 10 and -1 instead of 0. But that's still not what our comments say we should get. We've still got work to do on the code to make it do what it's supposed to do. We don't want to get ahead of ourselves though, so let's leave it at that. Once you're working through the exercises yourself in your Jupyter Notebook, remember you have to re-execute the class definition whenever you modify it. If you forget, the elevator variable won't change. If at any point you're stuck or something doesn't work as expected, there's more help in the next reading. Good luck! Wow, we've covered a bunch of new stuff in these last few videos. You're doing great. We've learned all about object-oriented programming and how to define our own classes and methods, including special methods like constructors or string conversions. We've also learned how to document them all. We're now going to talk about another aspect of object-oriented programming called inheritance. Just like people have parents, grandparents, and so on, objects have an ancestry. The principle of inheritance lets a programmer build relationships between concepts and group them together. In particular, this allows us to reduce code duplication by generalizing our code. For example, how could we develop our apple representation to include other types of fruit too? Well, one thing we know about an apple is that it's a fruit, so we could define a separate fruit class. We also know that all fruits have a color and taste. So what if we moved our color and flavor attributes into the fruit class? Here, we have a fruit class with a constructor for the color and flavor attributes. Now we can rewrite our apple class and easily add another fruit into the mix too. In Python, we use parentheses in the class declaration to show an inheritance relationship. For our new fruit classes, we've used that syntax to tell our computer that both the apple and the grape classes inherit from the fruit class. Because of this, they automatically have the same constructor, which sets the color and flavor attributes. You can think of the fruit class as the parent class, and the apple and grape classes as siblings. Let's see this in action. First, we create an instance of the apple class.
Granny Smith equals apple, and we'll give it 2 parameters, green as the color and tart as the flavor.
And now an instance of the grape class. Then, to check that this actually worked, let's print the attribute's values. With the inheritance technique, we can use the fruit class to store information that applies to all kinds of fruit, and keep apple or grape specific attributes in their own classes. For example, we could have an attribute to track how much of an apple is left after it's partially eaten. Of course, this applies to both attributes and methods. If a class has an attribute or a method defined in it, inheriting classes will have the same attributes and methods defined in them. But we can also get them to behave differently depending on what we change. To explore this, let's go back to our piglet example and change it so that there's a base animal class. In this code, we've defined a general class called animal, which has an attribute to store the sound that the animal makes. The constructor of the class takes the name that will be assigned to the instance when it's created. There's also a speak method that prints the name of the animal together with the sound the animal makes. Then we have a piglet class that inherits from the animal class. We set the value of the sound attribute to oink in the piglet class, and that's the only thing we've modified from the original. Everything else is inherited. Let's see this in action. Let's define a new class that also inherits from animal. How about a cow class? Cool. And to finish, let's create an instance of this class to make it speak. So you can see that we can easily define new classes that inherit from the base animal class and use both the attributes and methods that the animal class provides. Pretty cool, right? Let's think of a different example, something closer to what you might be doing at your day-to-day job. In a system that handles the employees at your company, you may have a class called employee, which could have the attributes for things like full name of the person, the username used in company systems, the groups the employee belongs to, and so on. The employee class could have methods to do a bunch of things, like check if an employee belongs to a certain group, or create an email address based on the name and username attributes. The system could also have a manager class. A manager is an employee but has additional information associated with it, like the employees that report to a specific manager. Are you starting to get an idea of the power of inheritance? Inheritance lets you reuse code written for one class in other classes. Next up, we're going to talk about a different way of reusing code. We talked about how inheritance creates an ancestry for our objects. To check for this ancestry, we can use the is-a rule. An apple is a fruit. A piglet is an animal. They inherit the attributes and methods of their parent class, and so they allow us to reduce code duplication. But what if you have a relationship between classes where one class isn't a child of the other? Sounds confusing? Let's check out an example to get a better idea of this. Say we have a package class that represents a software package which could be installed on every machine on our network. This class has a lot of information on the software, like the name, the version, the size, and more. We also have a repository class that represents all the packages that we have available for installation internally. In this class, we want to know how many packages there are and what's the total size of all the packages. In this case, the repository isn't a package and the package isn't a repository. Instead, the repository contains packages. To model this within our code, the repository class will have an attribute that could be a list or a dictionary, which will contain instances of the package class. So for this scenario, we'll make use of the code in the other classes by calling their methods. This is what's called composition. Let's see this in action. We'll first create a repository class that starts with an empty dictionary of packages when it's created. The dictionary will have the names of the packages as keys and the package objects as values. Nice. We have our class, which starts with an empty dictionary of packages. You might be wondering why we're adding the dictionary in the constructor instead of directly to the class. The answer to this might be a bit tricky to understand, so let's go back to our Juicy Apple example to help make sure this is clear. We defined earlier a class called Apple and set some basic attributes for it, like color and flavor. All instances of the Apple class will be initialized with the values that we preset for those attributes. If we change the color of one apple from red to golden, we substitute the old value with the new one. And super important to remember, this action happens only for that particular instance. But what if, ew, this apple has a worm in it? What if we wanted our Apple class to also have a list of worms? If we created the list when constructing the class, then all instances of the Apple class would have the same exact list. So if we added a worm to the list, it would get added to the one list that's shared by all instances. To avoid this, we need to create the list at the time of creating the instance instead of when creating the class. By doing this, each instance will have its own list independent of the others. This happens with all attributes that are mutable. Because when we modify a mutable attribute, we're not replacing a value or another, we're changing the contents of the original attribute. In our repository case, the packages attribute is a dictionary, which is mutable. We'll be modifying its contents by adding and removing elements in it. If we created it at the class level, all instances of the repository class would use the same dictionary, and items added or removed would affect all instances at the same time. If that's still a bit confusing, don't worry, I was also confused the first time I came across it. Just take your time, rewatch this video if you need, and remember this rule of thumb. Always initialize mutable attributes in the constructor. So great, we've got our dictionary, but how will we add packages to it? We'll create an add package method. Now we can add packages to the dictionary. We could also write a similar method to remove the packages, but I bet you can work that out without my help. Let's do something more interesting instead. We said that the packages had a size attribute that holds the size in bytes that the software package requires. So, how could we calculate the size of the whole repository? We'd need to iterate over the packages contained in the dictionary, adding up all their sizes. I'd go something like this. We're going to add up all the sizes. So the first thing we need to do is create a result variable that we'll use to sum up the values. Awesome, we have our result initialized. We now need to go through all the packages in the dictionary. Remember, the keys are the package names and the values are the package objects. For our calculation, we only care about the objects, so we'll retrieve them with the values dictionary method. And now, for each package, we want to add the size to the result variable. Nice. We're almost done. We just need to return the result now. Take a look at the method we've just written. It's a method inside the repository class that's making use of the values method in the dictionary class, and it's accessing the size attribute in the package class. That is the power of composition. When we have other objects as attributes, we can use all their attributes and methods to get our own code to do what we want. Wow, that was pretty complex, huh? Chances are you won't get it the first time around. Most of us don't. So if you're worried you might have missed something, take your time to review the contents. We want you to feel confident before moving on. When you're ready, meet me in the next video, where we're going to talk about a different kind of code reuse, using Python modules. So far, we've been using the features that are baked into the Python language. The basic statements like if, for, while, or the definition of functions or classes are part of the language and ready for us to use whenever we need them. The same goes for integers, floats, strings, lists, and dictionaries. They're all part of the basic Python language because they're used so often. Of course, this isn't enough to get interesting things done. We'll need a lot of additional tools, like being able to send packets over the network, read files from our machine, process images, or who knows what you might want to do to make your work more effective. To organize the code we need to perform tasks like these, Python provides an abstraction called a module. Modules can be used to organize functions, classes, and other data together in a structured way. Internally, modules are set up through separate files containing the necessary classes and functions. Python already comes with a bunch of ready-to-use modules, and all these modules are contained in a group called the Python Standard Library. Let's see how we can use some of them. First, we'll use the import keyword to import the random module. This module is useful for generating random numbers or making random choices. Now that we've imported the module, let's use a function provided by this module called randint. This function receives two parameters and generates a random number between the two parameters that we pass. In this case, we're generating a random number between 1 and 10. As you can see, this function returns different numbers each time it's called. Pretty fun, right? The syntax used for calling a function provided by a module is similar to calling a method provided by a class. It uses a dot to separate the name of the module and the function provided by that module. Let's try using a different module. The datetime module. We use this for handling dates and times. And now, let's get the current date. If you're wondering why we have a double datetime, it's because the datetime module provides a datetime class. And the datetime class gives us a method called now. This now method generates an instance of the datetime class for the current time. We can operate on this instance of datetime in a bunch of ways. Let's check out a couple of examples. When we call print with an instance of the datetime class, we see the date printed in a specific format. Behind the scenes, the print function is calling the str method of the datetime class, which formats it in the way that we see here. We can also access the instance through its attributes and methods. For example, we can look at the individual parts of the date, like the year, like this. The datetime module provides more classes than the datetime class. For example, we can use the time delta class to calculate a date in the future or in the past. Let's try this out. In this case, we're creating an instance of the time delta class with a value of 28 days. Then we're adding it to the instance of the datetime class that we already had and printing out the result. This is just a sneak peek into what you could do with modules. You can also develop your own. We'll talk more about that in a later course. For now, just focus on using existing Python modules.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.